Our next speaker is Sudipta Sinha. He's a principal researcher at Microsoft Research, and he will be talking about spatial AI, and especially on topics that relate towards privacy-preserving issues.
So good afternoon, everybody, and thank you for the thank you to the organizers for inviting me to speak at this forum. I'll be presenting some recent work on privacy-preserving methods for spatial AI, and this is joint work with several colleagues at Microsoft and also in academia. So basically, at Microsoft, I work on in the HoloLens team, and in our team, we use the term mixed reality broadly to cover, the whole span or domain spanning from augmented reality to virtual reality. It's a term that was coined in the 90s. And, for us, Microsoft HoloLens is something that, we have built. It's an untethered mixed reality device that the main purpose of this device is to blend digital content, which we often call holograms, into the real world and lock them to the real world so that you get the impression of the digital content blending into your real world. So that's really the core, technology that we're building. And, really mixed reality involves several things coming together. So it's really enabled by advances in computer vision, machine learning, but also a lot of innovations on the graphics and display side. But I'm a computer vision researcher, and there are lots of perception and sensing tasks, which broadly we kind of bucket into two groups, which we call human understanding and environment understanding. So for example, in these images, there are users who are interacting with the holograms using voice and hand gestures. So recognizing the hand gestures is one of the primary modes in which you give input to the HoloLens. So, but I'm going to talk today mostly about environment understanding, which I also refer to as spatial AI. Beyond mixed reality, the broad area of robotics, autonomous drones, navigation, and even commercial augmented reality on mobile devices, all these different areas require some form of what is often called spatial mapping and localization. And the fundamental task here is to provide some kind of real-time situational awareness so that the devices or the systems know precisely where in the three-dimensional world they are, so the 3D position and the 3D orientation. So primarily in today's talk, I'm going to focus on camera localization. So, concretely to define this task, our goal is, so we are given, for a specific environment, we are given some kind of pre-computed map. And this map for us often could be like a 3D point cloud. And given this map and a query image, we are interested in solving the problem of, basically localizing the camera within this environment as precisely as possible. So by precisely, I mean, for indoor environments, we are interested in really like, low centimeter level accuracy and under a degree of error in orientation. So this is what we refer to as camera localization, and it's very fundamental to augmented reality, but also robotics and other areas. Now, so this is a video from one of our earlier projects, which is kind of showing a localization system in action. So the top left video is the sort of, this is basically the video input that is going into the algorithm. And if you look at the bottom right, the blue curve that you see is the trajectory that has been computed in real time using the localization algorithms. And the red dots that are appearing are the features in the pre-computed map that are being recognized and matched, and that's what is being used to compute the camera pose. Yeah. So, with a lot of, advances in robotics and AR, a large number of people in the community are now starting to really talk about some new there are basically some new concerns around privacy. And the main source of the concern is that when you run localization and mapping within these systems, they run in the background, and there is generally concern around the notion that these devices are recording you without you being aware of the fact. And then the question is also, to what extent do these systems record the data and store them for in a persistent way in the cloud? So with these, so basically this is sort of a new area, although privacy preserving methods are now being explored heavily in machine learning and computer vision. If you specifically look at localization mapping, this sub-area of computer vision has seen no prior work on trying to address such concerns. And this is really what motivated us in the last year or so to work on these topics. I'm going to briefly cover these 3 projects that we have done. The first project really looks deeper into this privacy risk, and we've developed actually a new kind of privacy attack, in a sense showing that this is a real problem that needs to be addressed. And then there are a couple of projects I'll mention where we developed some initial solutions to address the risk. So this is the project. This is a project we did with Francesco, who was our intern in Microsoft Research, and with his advisor Sanjeev and my colleague Singbing. And the basic idea in this project was we wanted to take these pre-computed point cloud maps, like the one shown in the animation on the top left, and we wanted to try and reconstruct a visually plausible image from this point cloud. Now, the reason we are doing this is because normally when people reconstruct these maps, they don't store the images along with the map. The images are discarded once the map is reconstructed. And what is typically stored are the point clouds and feature descriptors associated with the points. So our goal was to develop an attack to see if we could reconstruct the image of the scene from the point cloud. And this is what we were calling map inversion. And as you see in this example, this reconstructed image looks extremely detailed, and it is remarkable how much information we are able to glean just from this geometric data. So in some sense, the project showed that this attack was very much plausible. There was a lot of implementation details. We did this using a deep neural network, trained it on enormous amounts of data. But the summary was that indeed we have, we can use these neural networks to really reconstruct scenes. So this is showing another visualization where we provide the system with the precise poses of the camera, and we are basically trying to recreate the original video. So the rightmost frame shows the original video, and the one in the middle is basically showing you what we can reconstruct. So the summary, basically we did this with a very standard neural network architecture. It's called basically a UNet, or it's also often called hourglass networks. We put 3 of them in series, and it's using a combination of standard supervised training loss functions. We were able to train this network, with multiple GPUs. So everything here is standard, but we really it was remarkable how good this attack worked. So here are some examples on completely new scenes that the network has never observed these environments during training. But on a wide variety of scenes, you can kind of compare the images in the middle row with the final row and see that we are able to really recover visual content that we thought it's as good as kind of storing the images. So it highlights that there is really some notion of privacy that we need to address, which is what we then try to develop in these other projects that I'll talk about. But before mentioning that, there's sort of this subtle question now of if you take a systems view, there are sort of 2 different scenarios. One where your localization algorithm runs on a client device. So this is being shown on the left side. So in this case, for the system to work, the cloud would essentially send you a copy of the map data. And in this client-based scenario, what becomes important is to conceal the map data. So the privacy of the map data is what becomes the primary concern. There is the other scenario, which is shown on the right side. And here, instead of downloading the map to the client device, the client device is going to upload a query image or query image features to the cloud. And now what becomes important is sort of to keep the query image private from the cloud. So these are the two scenarios that we tried to address. And so in the next project that we looked at, we focused first on trying to figure out how to keep the map data confidential. So the goal was we need to do something to the map data so we can conceal the information and prevent this kind of inversion attack that I talked about. Yet we want to use the data. The data is essentially geometric. You want to somehow do camera pose estimation. So these are the two opposing goals that we need to satisfy. And the main inspiration was that we came up with a new map representation. The basic idea was to take a set of 3D points, and for each 3D point in your point cloud, pick a random line that passes through the point, and then discard the original points and only retain the 3D lines. So essentially, we turned our 3D point cloud into a random 3D line cloud. And then, so this is sort of a visualization of what this looks like. So we are essentially taking the map and obscuring it using this randomized transformation. And then with this transformation being done on the data, the main contribution we made in this project was figuring out a new way to calculate camera pose. So instead of computing camera, the conventional way of doing this is to take point-to-point correspondences. So a point on a camera image plane associated with a 3D point. This is the traditional setting. And there are numerous algorithms for computing pose in this setting. What we did essentially was replace these 3D lines with, 3D points with the 3D lines on the right side, shown on the right side, and came up with essentially a new pose estimation algorithm to calculate the camera pose from this new representation. And one of the subtleties here is that on the left side, you can see that a minimal problem can be solved using just 3 correspondences because each one gives you 2 constraints. However, in the one that we propose, each of our constraints is actually weaker. We get 1 equation from each correspondence. So now we need 6 of them to solve. So basically, there are some technical details here, but we explored different variants of this new pose estimation algorithm that takes advantage of additional information like known vertical direction and known scale. And what was nice was, we were able to take existing solvers that have been developed in the field for different problems and map them to the problem that we needed to solve. And in the process, we were able to basically come up with fairly computationally efficient methods to solve this new pose estimation problem. So in a follow-up of this work, what we then looked at was the cloud-based scenario. So now we reverse the situation. Instead of downloading the map to the cloud, so imagine that consumers using smartphones and tablets want to localize themselves within some kind of a virtual environment, would all essentially, the cameras on their devices will be taking pictures and uploading them to the cloud. Or depending on the design of the software, they might be extracting features on the phone and uploading them to the cloud. And the map in this case stays on the cloud. It doesn't, so there's no concern of privacy there. But now we need to ensure that the cloud platform does not actually try to reverse engineer those features to get back the image. So this is the new scenario that we are addressing. The client is going to extract image features, upload them to the cloud, and if there was an adversary in the cloud, the adversary would basically then be able to, again, apply those inversion techniques I talked about to recover the visual content of the image. So here, the kind of content we care about is if you are in a public environment, you're essentially going to record other people. And so the question is there a way to localize this camera without the cloud being able to figure out anything about the identity of the people in the scene? So this is the ultimate goal. So we want to hide the visual content, but we still somehow want to use the geometric information to do camera pose estimation. So how do we do this? Again, we apply a very similar idea to the one I talked about earlier. So it's a geometric trick. Now we apply the trick to feature points that are on the image plane. Earlier, we applied the trick on the 3D point cloud. Now we're going to apply the same idea to the points on the image plane associated with the query image. So for this red point, which is one of the feature points in the image, we now choose a random direction and construct a line passing through that point, and then we discard the point, and we only keep the line. So what is uploaded to the server is not a bunch of feature points. Instead, it's a bunch of feature lines. And then we figured out again how to compute camera pose, not from point-to-point correspondences, but this time we have lines on the image plane and points in the 3D world. And again, we have to relax this need for, we need more correspondences, more matches now, because in the proposed method, we are throwing away information. So to compensate for that, we need more correspondences. We need 6 instead of 3. But again, this method maps very nicely to problems that computer vision researchers have studied, but in a completely different context. And it's called the point-to-plane problem. And once again, if we exploit things like known scale and known gravity direction, you can make these pose estimation methods even more efficient. So in a sense, this is really what we figured out. And this is an example showing what happens with this new method. If you apply inversion, imagine this is a query image that was uploaded to a server for computing camera pose. If you use the conventional method, one could reverse engineer the content of the image, and this is the kind of result you get. You can perhaps recognize this person from this image. But on the right side is the results you would get using our method, where information to the background will still get revealed, but the features in the image that don't match to the map, those feature lines are not going to basically get revealed, which basically means that now when you try to reverse engineer the image content, you won't be able to reconstruct. You get these blurry image patches. And so we feel that to a certain extent, we have addressed this problem in the cloud-based scenario quite well. So to summarize, I've talked about a new kind of privacy issue that it's a relatively unstudied problem, and it's becoming more and more important as mixed reality and robotics becomes widely deployed in our real world. And to address these issues, we have explored a few new privacy-preserving camera localization algorithms, where we try to keep the map and the query concealed, but still compute the pose in a reasonably efficient way. There are many open problems that I think need to be addressed, and I'm happy to talk more with anybody who's interested. That's it.
Thank you very much, Sudipta, for this excellent presentation and fascinating talk. There are open problems, and for sure, and that will be something that I hope some of our colleagues here would interact with you, including myself. I was impressed by the quality of the image. You start off with the original ones, not anything else, not the computation aspect of it, but the quality of them. And I just wanted to comment. And I remember being at Microsoft Research once, and your HoloLens labs are amazing, and so this is a good thing to see. I'm going to, in the interest of time, just take one question that came on chat, and I'll read that out to you. Mm-hmm. And while I do that, you may probably stop sharing. And this question is coming from Nitilan, and he is asking a specific technical question. The point cloud would store the color information, or would it be just SIFT kind of age information? Is the solution using some form of GAN to fill in the unknown information? I hope you get the question.
Yes, I get the question.
Sure.
So the first question, answer to the first question is, yes, in order to use the point cloud for localization, typically we store a feature vector associated with every point, like SIFT. So SIFT is a 128-dimensional feature vector, but there are many others. They're quite high dimensional, and it is required. If you don't store the SIFT vector, then the points are, it will be very hard to localize against the point cloud. And the color information, if the color information is stored, then actually, as you can imagine, the attack becomes easier, and the image reconstructed is even more accurate. But what we basically figured out is that you can discard the color information because, if you want to kind of make your system a little resilient, yeah, you can drop information that is not needed. So dropping color and storing just SIFT would be recommended. But the attack still works, even if you don't have color. We did that ablation study in the paper. And the second answer to the second question is we, again, trained different variants of the network. And to get the best results, to make the attack as good as possible, yes, we used GAN and adversarial training. But even without GAN, the reconstructions were a bit blurry. But still, if you show them to a human, in many cases, they will be able to recognize. But yeah, and these kind of methods using GANs are really working well. And we saw the same thing.